today I want to talk about a liquidity mechanism for Gyroscope, which we call the Gyroscope ECLP, or elliptical concentrate liquidity pools. And so the main driver is capital efficiency, and that's why I made the title of the talk, elliptical eccentricity for capital efficiency, and you're going to see why. Quick reminder from last time, why do we even care about the liquidity network, and how does that fit with the other things that Gyroscope is doing? So we have these two components, right? We have the stablecoin and the network of liquidity pools, ECLPs, that benefit each other in different ways. The stablecoin acts, or is aiming to act, and is more and more becoming a central component of the liquidity network, the best route to go from any other asset to any other asset. And the liquidity network creates a secondary market for the stablecoin, of course. LP shares can also be used as collateral, but the liquidity network is also useful separate from the stablecoin, and has a value of its own. One interaction that's planned for the future is that when you have an asset, like two assets that are not stable against the US dollar, but are somewhat stable against each other, then you can use that LP share as collateral and use an over-collateralized vault. So essentially, the stablecoin is then, from its perspective, holding a non-stable asset, but an over-collateralized vault, just like with many other protocols. And this has some other advantages and can be used for yield, for example. So I'm doing this series of talks. This wasn't last week. This was Tuesday. This week I talked about GYD, the stablecoin, the design of that, and today I want to talk about the liquidity network. And then maybe there's going to be a third talk on some other mechanisms that we use in Gyroscope. And I kind of want to split this up into a theory and a practice section. So first I want to talk about, let's say, the motivation and theory behind ECLPs, why we think we need them and how they work. Then I want to give you this nice tool of liquidity density, which I think is a very good way of understanding different AMM shapes. And then I want to go a little bit more into practice and show you what we're actually doing with these ECLPs, how they are useful from a, let's say, financial or business perspective, how they grow the actual ecosystem. And I want to start with a quick refresher on constant function AMMs. I'm always checking the chat a little bit. Right. So here I'm not sure. This is the bonding curve research group, so I kept it relatively dense and compact. But feel free to interrupt me with any question. I guess depending on your situation on call, you may have to do this via chat. And so the whole thing started with the Uniswap curve, right? But from a, let's say, abstract point of view, the thing I'm going to talk about are constant function AMMs. So structure is you have some function, and what it does is it takes the balance of your first asset X in the pool and the balance of your second asset Y in the pool and maps it to a number. And then you want to keep that function constant. So what it means is that if you have some current balances X0 and Y0 and some trade amount that someone wants to trade, so this could be positive or negative depending on if they want to sell or buy, you compute an amount delta Y such that if you make these changes to the balance of the pool, the function it keeps the same value, and that's why it's constant function, right? And typically what we call this, the value of this function is that the invariant value, and typically called K or capital L, or in the ECLP we call it R. I'm going to show you later why. So in other words, you have this function, you have an invariant curve of this function, mathematical invariant curve, and this is the curve along which trading is going to happen. Now, of course, the kind of original one was constant product. So your function is just the product of the two balances. And this has a few nice properties. For example, it's invariant under scale. It also has some nice properties regarding portfolio value. The portfolio, the value of the two assets according to the current price in the pool is always half and half. That's an alternative definition for the constant function market maker. This does not implement concentrated liquidity, by which I mean that it provides trading along the entire range of prices. And of course, for some asset pairs, this may be what you want if you have literally no idea what the price is going to be. But for many other assets, once you have some idea where the price is supposed to be, you have a lot of impermanent loss, very high slippage for trader, and pretty low capital efficiency, because the amount of, so by capital efficiency, I mean the amount of liquidity of trading between two assets that's provided compared to the TVL of the pool. And of course, that was the reason why for many assets, we don't use Uniswap V2 anymore. And then came StableSwap, which we all know and hold dear. And it's defined by this other equation here. There's no overlapping windows. So there's a guy called Bahar, just admitting them and see if our security model works. What StableSwap does is, the motivation for StableSwap was of course, can we have something like constant product, but can we make it a little bit flatter for prices close to 1? And then for some reason that is like work outable, you get this equation here. So here the invariant is called capital D. The A is a parameter and it's the amount of amplification. So A equal to, I think, 0 or 1 would be just constant product, I think. And then A to infinity is it goes more and more to a constant price curve that always has price 1. And it looks like this. And so when you are close to 1 in StableSwap, of course, you have very low slippage, and that's the reason why it's used for stablecoin pairs very successfully, and also other price-related pairs. But you still have this property that some trading is offered towards price 0 and infinity, right? So the price is the slope of the tangent. So once you go here, you go towards price 0. Once you go here, you go towards price infinity, and here you're around price 1. And that makes the whole thing capital inefficient to some degree. Now, I usually get some questions when I ask this, and the question is always, well, isn't it great that you can trade at any price? Isn't that a feature? And I guess it is, but it also comes at a cost. And what I'm going to show you later is that I think concentrated liquidity is the way. It makes sense to just not have any trading at some prices instead of having some trading that will, however, have very, very large slippage. And it's essentially what the ECLP was born from was, can we improve upon this a little bit? Can we add constant liquidity, concentrated liquidity, and make it a bit more configurable as well? And then this is like the third curve I want to show, which is constant product with virtual reserve, also known as Uniswap V3. And what you do here is, so the constant product curve would just be x times y is equal to L squared, where L is the value of the invariant. Now you modify that a little bit and you add these offsets. It's look like this and this. And what these are going to do is essentially you can, they move the curve down. So you can use one of the curve that would actually only be accessible with higher asset balances within a certain range. And graphically, what this means is that you take a constant product curve and you move it down so that the places where it has some tangent alpha and beta, so these are the ends of your trading range, and you make it intersect the axis at this point. So at some point, your balances in the pool will have axis 0, so it's only asset y in the pool, or the other one. So beyond these points, you cannot trade. But what you get is much better liquidity between these prices. And that's, of course, very good. So you recover that price impact. And now if we combine multiple of these curves with different price ranges, we get Uniswap V3, where someone can just, so in Uniswap V3 is then called either a tick or a position. And you basically create one such curve. All of these curves are added together, and that gives the trading curve of the whole pool. And that's pretty good. But the drawback we saw with that was that it's a lot of effort to manage all of these different positions. So first of all, as a liquidity provider, you have to think about not just, do I want to provide liquidity or not, or within which range, but you also need to think about, oh, how many of these like little buckets do I want? Do I want to put it all into one big bucket, or do I want to structure it a little bit more? Something like that. So there's a guy called Bitcoin22 entering the chat. I'll admit them and let's see what happens. Fun times. Yeah. For context, we got Zoom bombed before. Essentially, the motivation for the ECLP was, can we get the best of both worlds? Can we get great capital efficiency from Uniswap V3? Can we have concentrated liquidity, so restricting price range, lower slippage for traders, therefore more trading and more fees for LPs, right? Because the capital isn't just sitting around because you have better capital efficiency. And then from StableSwap, what we would like is ease of use. If I join a StableSwap pool, I just put my money in and that's basically it. I don't have to think about managing my liquidity positions. I don't have to think about which ticks exactly do I want. This is all pre-configured and I can just put my money in and it's very easy to participate. And then I should add another thing to the ease of use, which is, do I have to update my liquidity over time? So in Uniswap V3, when prices change, I have to manually or automatically in some way go and update where I'm providing liquidity. This can also happen when prices change mechanically. So let's say one of the underlyings is yield bearing, then prices will always change because of yield. And in Uni V3, I have to adjust my liquidity and move it with the updating prices. So can I somehow automate that? And then there's the fact that maybe not everyone should think about where to provide liquidity on their own in this making interaction easy sense. Sean, you asked, can I take a moment to define capital efficiency? Yes, of course. And there are multiple definitions you could use. I have one thing that makes this, one way to make this very, very precise, and this is this liquidity density analysis framework that I want to talk about in a bit. One very simple way of defining capital efficiency is you take a price range and then you look at how much of the capital is actually traded within that price range and how much of the capital is reserved for being traded outside the price range. That's something you can just compute. And then, of course, you actually need to believe in the price range, right? So it's always like capital efficiency, assuming a certain range of reasonable prices within which the price will probably lie. But once you do that, you can just take the pool you're interested in, compute how much is outside that range, and then do the quotient. And actually, for many of the ECLPs, we deployed this, and we saw an improvement in capital efficiency of, that was like large. That was like 30% on that range. So MD is saying idle money is inefficient, money at work is efficient. Yeah, exactly. So that's something you can do. I think, and you're saying that's a great definition. It's the desired consequence of denser liquidity, aka capital efficiency, to reduce slippage. Are there other benefits of capital efficiency as well? Yeah, I would say it can go both ways. So high capital efficiency means with the same capital, you get less slippage, or for the same slippage, you need less capital and can maybe do other things with your capital. Right. And then, of course, if you are a liquidity provider and you offer better slippage than everyone else in your pool because your pool is better calibrated to the market, and people tend to trade through your pool, and so you're making more money. Right. I have this big overview table here where, of course, in the end, it will be that the gyroscope is ECLP is best in all categories. But I think I want to go through these rows one by one. And the first thing I want to show you is kind of the math behind the ECLP and the construction. And afterwards, I want to talk about capital efficiency. And so this is the trading curve. This is the equation up here. But I think there's a much easier way to kind of tell you what's going on. But this is like the solution in the like math professor's way, where you first get like a formula and then they tell you like why the formula is correct instead of the other way around. And so what we do is we take an ellipse, we rotate it, and then we move it. And then we move it essentially in the same way as you do with Uniswap V3 or the 2CLP, which is what we call this because we also have a variant of that. And then you move it such that you hit the axes at where the tangents are your price bounds. And so if you look at this equation just as a little teaser, maybe you see where this is coming from. So you have like something squared plus something in y direction squared equal to r squared. So this is the circle equation. And then what's going on inside these parentheses is the transformation. So A is a matrix that does a linear transformation that's gonna create your ellipse. So that relates an ellipse to a circle. And this value chi here is what you compute to get the right offset. But let me explain this to you step by step. So this is how you build an ECLP curve. You start with a circle, and the circle has a certain radius r. And if we go back in the whole construction, r will actually be our invariant, what we use as the invariant. And then you take the circle. What you can do is you can stretch it. That's the simple linear transformation here. And you can stretch it by a certain factor lambda. And actually what this lambda will do is it will define the amount of concentration you have within your price bounds. Then you rotate it. And what this rotation does is that it gives you the price where you provide the most liquidity. And then you move it. And the movement is so that you get the right price bounds. And so then what you got to do is, if you have a current amount of assets in the pool, you compute the correct radius here so that after this whole process, you end up with a point with a point that is your current balances. And so maybe you believe me when I say this is conceptually a little bit involved because you have to keep track of your whole like rotations and like your linear transformations, everything you're doing there, and how prices change when you do this. But in the end, it's quadratic equations and linear transformations, and so that's totally doable. One other thing is that this rotation here, there's like a sine and a cosine there, but we don't do like trigonomics on chain. Like we don't have to do this because you never actually have to think about this angle as an angle, but you can simply store the sine and cosine values, and that gives you everything you need to actually execute this rotation. And what you get then is a trading curve with some properties. So I talked about the price range, which is given by the slopes of the ellipse curve, where it meets the x and y axis. You also have this part. So this is the flattest part of the ellipse curve. And what it gives you is, it gives you the point where the amount of liquidity you're providing is highest. And I will make this precise. But maybe you can already intuitively see that when you move along this part, then the curvature of the ellipse or the slope does not change so much compared to when you move along here. And the price there is configurable. It's I don't know if I have this here. It's the tangent of the angle. And again, we don't need to do trigonomics. We simply use the S and C values and then compute that, or vice versa. And then what you can do is you can stretch the ellipse. And now I'm really kind of asking for your imagination. So if you have a larger scaling factor, when you stretch the ellipse from a circle, what you're doing is you're making it longer and flatter, which means that you have prices close to this peg price for longer. And if you do that less, you have more of a gradual transition between these 2 points. And so the way how you can use that is you can shape within my trading range, where do I want the liquidity? Do I want the liquidity pretty much evenly spread out, or do I want it very concentrated towards this peg price? And I'll show you an example in a bit. And so this is not exactly the same as eccentricity of an ellipse, but it's the same. There's like a one-to-one mapping to eccentricity. I think eccentricity is usually between like 0 and 1, and this parameter lambda is between 1 and infinity. Right. I should have said another thing. Oh, Mark Richardson was praising ellipses. That's amazing. Sean, can you tell me how Mark was praising ellipses? By the way, I can also give you like I can also unmute you if you want. Okay.
Thanks, Steffen. Can you hear me all right?
Yeah.
So I can't say a lot because I can't say I fully understand what Mark was illustrating. It was in the construction of one-sided bonding curves. So in this carbon protocol, you know, you have a market for trading X versus Y, and it actually creates two independent bonding curves, one for X, one for Y, and somehow maintains the market. I still need to review the materials, but in leading up to this construction, he said, you know, he gave us a lot of hints that ellipses, and he in fact showed us some simulations that utilize ellipses, but in particular, he dropped resources. He dropped a few educational resources, YouTube videos that I'll share with you. We'll even put them in the show notes for this call, illustrating ellipses. So I've just been going down that rabbit hole of trying to get my head around it. And now here you are showcasing them in, you know, kind of what looks like a more direct, more simple, but also more applied way. You're directly utilizing the ellipse as sort of the core of the mechanism. So really cool to see that.
Cool. Yeah, interesting. Yeah, I would be very interested in that. So I mean, the motivation for me and for us to use ellipses was really just that they are configurable. They have a bunch of parameters that you can use, and you can still compute it on chain because in the end it's basically linear and quadratic. Great. Right. So I think I was talking about why we are using ellipses. And for us, the motivation is really because they are configurable and easy to implement and do pretty much. I hope I will be able to convince you of. I should talk about one more thing that we can do that's kind of orthogonal to this whole trading curve and ellipsis stuff, which is rate scaling. So let's say, and this is something that's needed for yield-bearing assets. So let's say you want to make a pool of, let's say, some token against SI, which is something we do. So SI is non-rebasing yield-bearing version of DAI invested into the DAI savings rate. And so what's going to happen is that the price of SDAI over time is going to go up because that's how it accrues yield. Of course, you can redeem it for DAI. But if you were to use like these things, let's say raw without any further adjustments, at some point it would just leave your trading range and it would always hit the end of your trading range. And so to compensate for that, we have built in this idea of rate scaling. So what this means is that there's a smart contract somewhere out there. It follows the rate provider interface, which basically means it has a function that's called getRate, and it just gets a number. And before anything happens, the balances of the tokens are scaled by the rate that's pulled from the rate provider. And so for SDAI, for example, what this rate provider does is it gives you the current amount of DAI that you can redeem from 1 unit of SDAI. And what we can do then is that these price ranges now don't correspond to the SDAI 2 GYD price, for example, anymore, but to the price of DAI underlying SDAI versus GYD. Or for liquid staking tokens, we have a pool of wrapped staked ETH against wrapped ETH. And we use the same technique. And now the price is wrapped ETH contained in a unit of wrapped staked ETH versus wrapped ETH, which is basically the same as staked ETH against, so staked ETH being the rebasing version. Staked ETH against ETH, there's kind of a technical reason why we don't just use staked ETH, namely that we're based on Balancer, and the Balancer vault doesn't support rebasing tokens because it does its own internal accounting, which is very useful, but which prevents you from using rebasing tokens. So we do that instead. And it's also pretty convenient because it gives you access to a wide range of asset pairs that you can use with this rate scaling. I think now what I want to do is do like a little bit more theory and then do some practice. And what I want to talk about is this liquidity density tool. And essentially the motivation was, how can we compare these different curves? And of course, what you can do is you can just look at it. But then once you are looking at, let's say, stablecoin pairs or liquid staking token versus underlying pairs, what's your trading range going to be? It's going to be very close around 1. And what this means is that all of your slopes are going to be very close to 1. So this is like not the right picture for that. But in the picture, a human just wouldn't be able to see any difference because we're not very good at understanding tangents. And so we thought, okay, let's say depict it differently, and then it's also kind of a useful analysis framework. So I'm just defining liquidity density at some point is the derivative of asset Y as a function of the price. By price, I mean the relative price of asset X, to an asset Y, the way the pool sees it. And so I'm using the kind of the physicist's notation for these derivatives here, which is like, I'm not marking what is a function of what changes or something like it's like everything changes in one big dynamic system at once. And what I mean by this is, well, what this means is that this is the amount of asset Y that you have to trade to change the price by 1 unit in a marginal sense. But in a non-marginal sense, right, if I change the price by +1, this gives me the amount that I have to trade. And you can do a relative version of this. If you put the log here, then this, in a marginal sense, is how much can I trade to change the price by 1%. And then, but these are very closely related because like this thing is just this thing multiplied by P. For the rest of the talk, I'm going to ignore this relative version because I'm mostly interested in assets where the trading range is already very close around 1. And so you are making a very tiny adjustment when you're switching from one to the other. So they're going to be basically the same. And now why is that like a good measure of, why is it called liquidity density, right? So I think it's a good measure of liquidity because high liquidity means you can trade a lot without changing the price a lot. Meaning to change the price a little bit, you have to trade very much. So if this value is high, then this means you're offering very high liquidity at some point. If this value is low, vice versa. If the value is low, you have a lot of price and spread slippage over things that are kind of bad for traders. Right. And now let me show you some liquidity densities. And here are some of them. So the first thing I want to show you is, so what I did here is I took a price range. So the lower one is alpha, the upper one is beta, and the units are basis points from 1. So this is like 1 minus 0.003, and this is 1 plus 0.003. And these would be like typical price ranges that we're interested in. And then I took a bunch of AMM curves and I calibrated them such that the TVL at price 1, so that's exactly in the middle here, or 0 basis points, is 1 million. And now I plotted liquidity density. And the simplest thing we can do is 2CLP, or Uniswap V3, a single Uniswap V3 bracket. And this gives you a liquidity density curve that's not flat, but that's almost flat. So I think the function is 1 over square root of p, where p is very close to 1, so it doesn't really change. So this is almost constant in this price range. And then you can do StableSwap. And StableSwap gives you a curve that's peaked, so it looks like a little bit like the bell curve, and of course the ECLP one does too. And how much peaked it is depends on the amplification parameter. So if your amplification parameter is low, then you get this like slide, like hump at 1. And if it's high, then you get this like really big peak. But it's also infinite. So it like goes infinitely far in both directions. And of course, that's exactly the capital efficiency problem that I was talking about. The StableSwap offers trading at prices where you may not need to trade.
Steffen, can you remind us what is 2CLP?
Oh yeah, right. So maybe I should talk about that more. So a 2CLP, actually the ECLP is actually the third iteration of pools that we made. We have 2 more. So a 2CLP is a single Uniswap V3 tick. So essentially this AMM, constant product with concentrated liquidity. And we call this the 2CLP. So it's a concentrated liquidity pool with 2 assets and almost flat liquidity density. We haven't been using this very much in practice, but that's like half a coincidence. So we have some things planned where the 2CLP could be useful and this flat shape could be useful. For example, one thing we are considering is to do pools of, let's say, S-DAI versus DAI. So that's the same pair you would get by just going through S-DAI's mint and redeem mechanism, but it costs less gas and providing liquidity among these pairs where there's actually a very, very strong peg between the 2 constituents, but you can save some gas by trading instead of minting and redeeming in the protocol.
Neat. So a question follow-up. Would a 2LP have a flat density curve?
Yes.
Okay.
Yeah.
Okay.
Yeah.
Gotcha.
I mean, it's not exactly flat. It's almost flat.
Wow.
Imperceptibly growing.
Wow.
Or declining, one of the 2.
Oh,
I thought about a flat liquidity curve, and I think it's actually pretty easy to construct. I mean, what you do is you just go to this definition, assume it's constant, and then you can do the other direction. You can integrate, and then you get the one asset as a function of a price, and you throw some other assumptions in there. And actually did it, and what comes out of that is some kind of exponential curve, I think.
Interesting.
I think it's like an exponential decrease with certain like parameters, like a weight in the exponent and stuff like that. And so yeah, you can definitely do that.
Great. Follow up on this slide. You said with a relative liquidity density indicates we can say like a 1% change
Right.
in price. Where do you get that from?
Because I'm taking the derivative against the log. So
And
if the log of the price changes by okay.
maybe remind me, the derivative of a log is that 1 over, would it be, is this, oh no, sorry.
Yeah, right. So do I have this somewhere? It's like the super basic thing I also it's like you're not you're not like incompetent or something. So okay, so this is how you do relative changes. So if you want to know how much something changes when you change something else by some factor instead of when you're adding something to it, then you do the derivative against the log, and this is just short notation for like, or I mean, whatever, right? The first is probably find this meaningful, but it's just like
I remember this from my machine learning class.
yeah, right. So this is just divided p, and then divided by this thing, and then this is like 1 over p, and that's why the equation is the right thing. And now why is like this formula the right place to start? Well, if let's say you go from so let's say log p prime is equal to log p plus some delta, and that's the same as saying log p. Now let me hope I'm doing this right. Log p times x delta, right?
Mm-hmm. Mm-hmm.
That's correct, because logs adding stuff. And then I'm just removing the
Yes.
log p times x. And now I'm just removing the log, and now that's equivalent to this. Okay, and so when I'm adding a little bit to a log, that's the same as multiplying the underlying value by something. And so if I take a derivative against the log, that's the same as taking a derivative with respect to multiplying the price by something.
Great.
That's why that comes out of that.
Steffen, can you go over the equation one more time? Oh, sorry.
Sorry?
Can you go over the equation one more time?
Oh, yeah, sure.
Like how you...
This definition or this one?
Yeah, the one you typed. Log
Oh,
p
yeah,
prime.
yeah, sure, of course. So what I wanted to do is motivate why the relative liquidity density, so how much does y change if you change p by some factor, why that is the derivative of y against the log of p. And the motivation would be, so if I change the log of p by some absolute amount, then I can reformulate this as this. It's just pulling two logs together. So I'm writing like delta as like log of x of delta. And now I know that log is strictly monotonic, so I can just remove it. And it's still equivalent. And then I get that these two things are equivalent. And so if I change the log of the price by some absolute amount, then this is the same as changing the price by some relative amount. And of course, there's this x between the absolute and the relative amount. So it's not the same. It's like a nonlinear scale. But it should do the right thing. Okay. Should I continue?
Yes, please, Steffen. Thanks for
Oh,
that.
yeah.
Very
Thanks for
powerful tooling there.
Yeah, sure. Right, and now we can kind of look at these curves again. So we have the 2 CLP. By the way, we also made a 3 CLP, which didn't see any application yet, but which I would be very excited to deploy. So a 3 CLP is the same thing, but with 3 assets, which actually happens to be kind of difficult to really get right. But we did it. And right, and so if we compare these liquidity curves here, we can see that the ECLP has concentrated liquidity. It has the peak here. So again, that corresponds to the rotation of the ellipse. If you rotate it more, this will move up, I think. If you rotate it further, if you rotate it less, it will move down. What you see is that the ECLP also has this peaked shapes. For the StableSwap curves that I chose, it's that it offers vastly greater liquidity for most of the prices. I mean, you have to compare this along this axis here, right? And then a little bit less liquidity towards the end of this range. If you feel that this is not what you need, you can adjust the lambda, which is the amplification parameter, and just stretch the ellipse less. And then you get a liquidity curve that's less peaked, less concentrated, and that allocates more evenly towards the whole range. But you still get some structure within the trading range, whereas with the 2 CLP and these kinds of curves, it's always flat. If you want to look at this blue liquidity density here would be a single Uniswap V3 position. Of course, in actual Uniswap V3, you have many positions that are kind of put next to each other, and the liquidity density of that would be and I didn't plot this. I could have, but I couldn't handle my Python right. But it would be like a little histogram here. So you have many little pieces that all are their own trading range, and that can emulate basically any curve you want. So if you let the number of pieces go to infinity, you can have any shape you could possibly want. It's hyper flexible. But of course, while you do that, you also have much greater costs for let's say administration of the whole thing. And it seems so. If you look at the actual resulting curves in these Uniswap pools, for some assets, they are actually more or less bell curve shaped. Of course, not exactly, but people have put in some effort to get to some shape that is kind of like this, or different people have put liquidity into different places, and then it just kind of happened to be some kind of bell shape. But of course, you always have a grid, right? You have perfect smoothness and everything. You don't get this for free, whereas with the ECLP, it just happens to have a curve of this shape, and it's not like you have to pay a lot of gas or anything to get to this curve. It's just a matter of configuration.
Super cool. I had a couple of questions. Unfortunately, I've got to jump. I've got a client call kicking off now. But I have a couple of questions. One, can this be applied for more than 2 tokens? The ECLP equation is my first one. And the second, is this dynamic at all, where the range of that liquidity can shift as needed? This is amazing.
Right. So my one answer is more than 2 tokens seems difficult. It seems like it should be doable in principle, but you have to kind of redo the math. Would be super interesting to do this. What you can definitely do is you can do the thing with the meta pools that balance it for a while and came up with WellGo, or Curve is also doing this, where you have a pool and it holds as one of its assets the LP share of another pool, and then you can swap through it.
Right.
It seems to be a matter of technical infrastructure, but it's not a fundamental thing. The other question was like, can you do it dynamically? Right now it's static. We want to make a dynamic version of that. I think that could be very cool, and you're probably already like taking away some of the use cases I wanted to go into. So for example, when you have stablecoins with mint redeem mechanism, there's like the interconnection to the dynamic stability mechanism I talked about last time, and access the current state of that mechanism in your secondary market and optimize the secondary market for that. That is currently not happening. The main reason is that when you change these things, you have to be super careful not to create any arbitrage opportunities. I mean, I think Curve had this a while ago where they just allowed updating the amplification parameter, but then you're basically, it's very easy to exploit this when you know when an update is going to happen. And so you probably have to do it like slowly over time. The other thing we need to make happen to move this to chain, which again is like not an impossibility, but just has to be done, is moving some computations to chain. Because right now some pre-computations actually happen off-chain to support the efficient execution. So like this is not happening during swapping, but it's happening during like setup of the pool. So you have to provide some pre-computed values to the pool. And the pool runs a few checks. Right, so that would have to be moved on chain to be meaningfully dynamic.
Makes sense. Cool. Unfortunately, I have to run. If you're still going to keep going, I'm definitely going to follow up on the recording.
Sure. Yeah, absolutely.
And I'm looking forward to our next session as well, because there's so much to unpack here. This is such cool stuff.
Thank you, Jeff.
Thanks so much.
I have one more question. I'm gonna follow up. Thanks, Jeff. Okay, thank you, Steffen. Awesome. I do have another meeting, but I just told them I'll be a few minutes. I have one question I want to ask, which is there a property here, like the area under these curves? Would that quantity be constant across the different curves, or maybe not? And just the general integral, does it have meaning here?
Right. Yeah, that's a great question. So if you take any finite integral, then let's say between price A and price B, then that's the total amount of asset Y you have to trade to move the price from this point to the other point.
Oh, yes.
And so in particular, what this means is that if you, so these things are meaningful. If for the ECLP, if you, and that would also be the case for any concentrated liquidity pool. If you take the integral across the whole range, and that's the maximal amount of asset Y that you can have in the pool. So that would be this value up here.
Gotcha. Interesting. Yep.
But you have, of course, you have infinite curves. There, I don't know. I mean, I guess the integral is then infinite. I'm not super sure.
Oh, I guess I don't think it would be, or would it? We'll have to find out.
Yeah. Right.
Great. Thanks for that. Just such fascinating results. And I mean, you're in a position, you got some bragging rights here with this chart. This looks pretty good for the ECLP.
Yeah.
It's pretty interesting.
Thank you.
Yep. Okay, great.
Okay, awesome.